Right, section 8.3, vector, parametric, and symmetric equations of lines in 3 space. Okay, so our third component, x, y, and z this time. You're going to find that all the definitions for vector, parametric, and symmetric equations hold. We're really just very simply just working with the third component, and we deal with the third component exactly the same way we deal with x and y. So the vector equation is defined here by our vector equals our point. Okay, I'm going to clean this up a little bit here. I want to make sure that I have this right here. So this vector, okay, this really is a point, right? Now it's written as a vector, okay, because it would be a vector from the point to the origin, right? So it'd be the point. If it was a point, okay, it would be the point OP here, and then we still have our parameter, and we still have a direction vector. So let's find a vector equation of a line that passes through the points A and B, and can there be more than one vector equation? Okay, so we're going to find our direction vector first. Okay, that's going to be AB, okay, and that'll be -3 take away -1. It's -3 take away +1, right? So that'll be -2. 3 take away 3 is 0, and -4 take away 5 is -9. So that's our direction vector and our vector equation. Then I need a point, right? I need a point. I'm going to use point A. Then I introduce my parameter, and then I tell the vector equation exactly what direction to go in to get my next point here. And I need my, okay. Now I could have chosen a second point. Okay, I could have chosen point B, a perfectly fine answer. And I'd use the same direction vector. Okay, and I'd also have the same parameter. Now I could have, and what I'm doing by showing a couple of different examples is answering the second question, right? Can there be more than one vector equation? Yes, there can be. Okay, I've just written 2. I could have easily found BA, that's the same direction, be different, the values would be different, it'd be 2, 0, and 9, right? But I could use that direction vector to generate 2 more, right? Because each of the points I could be used with this second direction vector, and that would represent the same line, right, by way of a vector equation. So we have a variety of vector equations. When I'm given a situation of a line in 3 space, a couple of points or direction vectors, I can write a whole bunch of infinite number of vector equations, right? That makes, I think, some sense based on our work with Cartesian graphing, right? That if we've got a line, we've got all kinds of different equations for it. Similarly, our parametric equations are the same. Okay, so let's do the same. I think it was the same example here. I'll just reach back, and no, it's not the same example. So I'm going to have to write. Let's go D again here, and that's going to be vector AB. So I'm going to go 1 take away 0. That's 1. -1 take away 1 is -2, and 3 take away 2 is 1. So my vector equation, I'm going to write first. That'll be 0, 1, and 2, plus then my direction vector, and then I asked for a parametric equation, so I just have to expand this. So x equals 0 plus t, y equals 1 minus 2t, and z equals 2 plus t. Now the only one that I would write a little differently is x equals t here. And I should always put this definition of parametric equation, right? That allows me to make this line solid when I talk about it. All right, symmetric equations. Well, it's the same here. It's the same. So it's really not a big deal. So let's, yeah, I don't think I left an example here. Oh, okay. But I want to make sure I didn't miss any examples at the bottom tail end of these. All right, let's get into this one. Convert the vector equation into parametric and symmetric equation. Okay, so I've got vector equation given. I'm going to write in a parametric equation. I'm just going to call this PE. would be x equals, now I'm going to drop the 0, okay, so I don't need 0 minus t. I'm just going to write minus t here. Y equals 1 plus 2t, and z equals negative 3 plus 0t. Negative 3 plus 0t. Negative 3 plus 0t. And I'm not going to write my 0t. Okay, I'm going to clean that up a little bit. I don't know what happened there. But okay, it's just 3. Okay, now my symmetric equation, okay, remember what I do here. I rearrange for t, okay? I rearrange for t and write them all equal to each other. So when x equals t, negative t, x equals negative t, t would equal negative x. Okay. T, when I have my y component, okay, that would be y minus 1 divided by 2t, that's x. Okay, and then I don't have, okay, I'd have z minus 3 divided by 0, okay, and I don't, okay, that's a no-no here. So I'm just going to have to write z equals 3. Now, my symmetric equations, then, okay, I equate my t's. So I'd have negative x equals y minus 1. Okay, but I can't do, okay, anything with z. I don't have z in terms of t. I just have z equals 3. So that's exactly what, okay, you'll see in the textbook here, where the symmetric equation, okay, is sort of partially written right here, but then I just write this extra z equals 3. And what this means, okay, is that there's a point here, okay, okay, z equals negative 3 along, okay, this, okay, it's in this plane basically. We're going to talk about this in a little while here, okay. So now you might see different instances where it'll say no symmetric equation. Okay, it's not a formal symmetric equation, right, because there's not 3 ratios that are balanced here. Okay. Now determine next example here. If I'm given a point and I want to see if it lies in, okay, each of the lines that are given here. So let's take the first case here. So I'm going to put the point 1, 4, and negative 7 into my equation. 1, 2, negative 3 plus, and then I just expand, right? 1 equals 1 plus 0t, 4 equals 2 plus t, and negative 7 equals negative 3 minus 2t. And I solve each for t, right? Okay, in this case I've got, well, 0 equals 0t, and t can be anything. Okay, so that really doesn't give me a solution. It actually gives me a full solution. Any value of t satisfies this equation. In this case, I've got t equals 2, and in this case, I've got negative 4, negative 2, and also t equals 2. Okay, so I do have a consistent system here. Okay, I do have a consistent system. We'll talk about the x component in a second here. But when I have a balance, right, then my point 1, 4, and negative 7 lies on the line. Okay, so I do have balance here. This allows for everything. When t can be any value that'll satisfy this equation, including t equals 2, right? Then I've got, okay, that's sort of a catch-all statement here. Now what about the next one? Okay, my point is 0, 1, and 5. And I've got, okay, that equals, oh, it's in a parametric equation form. Okay, so I already, okay, I can put in, okay, my value of x is 0, negative 2 plus 3t. Okay, and my value of y is 1, and according to my parametric equation, it's negative t. And then my value, okay, is 5. Okay, my point is 5, and my z value is 5. Okay, so that's good. That's a clear, okay, that's a clear balance here. Okay, let's solve for t for the other ones here. Okay, so 1 equals negative t. Okay, so t equals negative 1, and let's see if that works in this one here. So I'm going to put in, I'm going to rearrange my equation for t. No, it doesn't work, right? it's an inconsistent system. Inconsistent solution. So therefore my conclusion is that my point 0, 1, and 5 does not lie on the given line here, okay, because there's an inconsistent. I get t equaling two different things in each case here. All right, let's talk about some specific lines. Now, these are discussed in the lesson and in the textbook, but we've got some specific lines here. Oh, I think I cancel. I'm going to cancel that. Let's get. I don't want to do this necessarily, so I'm going to try and. Okay, I'm going to pause this and get back to. Let me just close this down here. Okay, I'm going to try and deal with this later here. Let me finish my video here. Okay, so some specific lines I've got. Okay, lines that are parallel to the x-axis. Okay, have a component in the direction vector will have a component in the x, and the others are 0. Okay, and that's when it's parallel to the x-axis. It means that it's perpendicular to the y-z axis. Okay, similarly, lines. Okay, got a line with a u direction vector where there's two components. Okay, in the y and the z, it means it's parallel to the y-z axis. And this is what we're talking about here, this y, x, y, z axis and plane. Okay, so let's go through a couple of examples here that talk about, okay, some of these examples here. Let's quickly go through, okay, some of my answers. Okay, so I've got to write a vector equation of a line that passes through the point. So there's my given point, and it's parallel to the y-axis. So if it's parallel to the y-axis, I've got a direction vector. Okay, my most basic direction vector is the direction vector 0, 1, 0. It's parallel to the y-axis. Okay, so my vector equation is my point. Okay, it's my given point. And then my direction vector. Okay, next example, it's perpendicular to the YZ plane. So if it's perpendicular to the YZ plane, it's going along the x-axis here. So my most basic direction vector is this. Okay, so my vector equation would be -1, 0, and 4 plus p 1, 0, and 0. Okay, passes through and it's perpendicular to the x-axis. Now if it's perpendicular to the x-axis, it's coming off the x-axis, right? And my direction vector is in the y-z plane. That'll be this vector, or sorry, this direction vector, and I've got then my vector equation that represents this situation. It's got to go through the point, and then it follows along. Okay, along this direction vector. Okay, and then finally, an example of a vector equation that passes through the origin. And then follows along the x z plane. And the x z plane, if it's it's parallel to the x z plane, so it lies in the x z plane, and that would be this direction vector here. So that goes here. All right. Okay, that's kind of a quick way. It's better explained in the textbook and the chapter, okay, and the online lesson. But if I've got parallel to the y-axis, okay, it's going along 0, 1, 0, 0. If it's perpendicular to the yz plane, okay, perpendicular to the yz plane, it means it's going along the x-axis. That's 1, 0, 0. If it's perpendicular to the x-axis, that means it lies in the yz plane, and that's the direction vector 0, 1, 1. And if it's parallel to the xz plane, okay, it means okay, it lies in the xz plane, and that's 1, 0, 1. All right. Intersections. Okay, a line that intersects the x-axis has the point, okay, y equals 0 and z equals 0. A line that intersects the xy plane has z equals 0, okay, as it's set, okay, a value here. And we've got a pretty good example here. Consider the line 3, negative 2, 3, and the plus t, negative 1, 2, and negative 3. Find the intersection of the points between the line, this line, and the coordinate axis and the planes. Okay, so each of the coordinate axes and each of the planes. Okay, so let's do the coordinate axis first. Okay, so that would be okay, the x-axis. Okay, and the x-axis, it's going to intersect at the point x 0, 0, and I'm going to set, and I'm going to try and solve for, okay, so x equals 3 minus t, and I've got 0 equals negative 2 plus 2t, and then I've got 0 equals 3 minus 3t. Okay, so in this case I've got, that was a minus. Okay, so 2 equals 2t, t equals 1. Okay, in this case I've got same thing here, t equals 1, and that's a consistent system, and I'm going to put that over here. So x equals 3 minus, I just found t equals 1, so x equals 2. And the point then that it intersects the x-axis is 2, 0, 0. Now I'm going to let you guys work through each of the other ones here, the y-axis, okay, and plug in the point 0, y, 0 into my same equation, and then solve just like I did up here. And for the z-axis, it's the same. I let the point 0, 0, z okay, equal my given equation of my line, and I work it out just like I did for the x-axis. Okay, pause if you want here. I'm going to put the answers up on the board here in a second. Okay, you should find, okay, when you complete these and find these, that y intersection, it doesn't intersect the y-axis. There's no solution here. Okay, so our line does not intersect the y-axis, and okay, I also found no solution for the z-axis. Okay, so basically it falls down. There's an inconsistent solution in that type of thing here. We're only half done this question. This is a large question here, because not only that, if I found where it intersects the coordinate axis, I've got to find out where it intersects the planes. Okay, so for the planes, I've got 3 planes here. Okay, and I'll walk you through, okay, one of these solutions. Let's do the xy plane here. Okay, so for the xy plane, I've got to solve this equation. Okay, so I've got to find values of x and y. I do it the same way. Okay, but I'm going to do a little, okay, bit of a different step here. Now, notice the only one I can solve here is the z component when z equals 0. So I'm going to work on that one first, and that's going to be 3 plus 3t. Okay, so when 0 equals 3 plus 3t, t equals negative 1. Okay, so negative 1 is the value here for my parameter that makes this click. So that's going to allow me to solve for x. and it's going to allow me to solve for y. Okay, so x equals 4, okay, and y equals, so I let t be the value that I just solved, and it looks like I've got -4. So it intersects the xy plane, okay, at the point 4, -4, and 0. Okay, so I'm going to let you guys solve each of those ones as well, too, the other ones, and I'm going to work on those solutions as well here. So I'm going to pause this and come back to you in a minute. Okay, so I got for the, what was the next one, the x, z plane, okay, trying to solve it the same way. I got the point, okay, sorry, the plane. No, it's a point. Okay, it's 0.200, and it intersects the xz plane at this particular point. And for the last one, the yz plane, okay, solving this simple little system, okay, the point. Okay, now I think looking back on my solution, okay, I think I made a pretty grave mistake here. It had a -3 in the question, but it looks like I solved it for some of it, but then dropped it in here. Okay, so that's a bit of an issue here. I'm going to change it to plus. Okay, I'm going to solve it here, plus, that'll be plus, plus, okay, that'll be a -1 here, and then I get an inconsistent. Okay, if that was the case here, I get an inconsistent solution here. Okay, either way, the steps are the same. Okay, I think I just made a simple little mistake writing the question down here. All right, let's move on to angles. Okay, so angle situations here. Determine how these two lines intersect by way of angles. So now we've done a question like this before. It was in 3 space. So what I need here is my direction vector. Okay, that'll be -1, 0, 0. My direction vector for the next one is 0, 0, 2. My angle formula, okay, is the same no matter if it's third component or not, doesn't matter. Okay, so I've got, okay, dot product, right? Okay, -1, 0, 0, dot that with 0, 0, 2, okay, and that's going to be over the magnitude of d1, okay, which is, okay, -1 squared plus 0 squared plus 0 squared. And then the magnitude of d2, okay, which is 0 squared plus 0 squared plus 2 squared. Now, dot product here, okay, would be -1 times 0, 0 times 0, and 0 times 2. And that's going to be 0 over square root of 1 and square root of 4, which we know to be 0 over 2. Either way, it's 0, right? And if the cos theta is equal to the 0 ratio, okay, then I have perpendicular lines. Okay, so the angle between these two lines is 90 degrees. They're perpendicular, and that's how I kind of work through that. Okay, now I have to find, okay, it asks me, I think, to actually find this point of intersection here. So really quickly, okay, I'll finish this off. Okay, so my point of intersection, okay, is when I equate the exponents here. So let's expand, okay, each of, okay, the first line. So the first line, I'm going to expand it to, okay, x equals 0 minus s, y equals 0, okay, and z equals 1 plus 0s, right? There's 0 s's here, there's a 0 s here, there's a 0 s here, and in line 2, I'm going to expand this by components. So x equals -3 plus 0t, nothing, right? Okay, when there's a 0t, okay, there's nothing there. The next one, okay, my y component for my second line is 0 plus 0t, 0, and z equals 3 plus 2t. Okay, now I'm just going to verify. I just expand. All I did is expand these out by components here, x, y, and z. Okay, now compare the x's, compare the y's, and compare the z's. Well, it looks like I've got balance here with my y's. That's good. I've got a consistent solution here. Can I solve for any of these? Okay, can I equate? Let's equate my x's here. Okay, so let's equate these two, my x's. So in line 1, I've got 0 minus s, and in line 2, I've got negative 3. Well, that's good. That allows me to solve for s equals 3. Okay, so s equals 3 satisfies x and y, and there's no s component or s parameter in the z component, right? So that's fine. I think I've got my system here. So if s equals 3, okay, that might be my point of intersection here that balances this equation. Let's find it when okay, let's solve for z here and see if we can get a value for t. Okay, so either one will work here. I can either let s equal 3, okay, in my first line, that'll give me my point of intersection, or I can equate my z's. In this case, it would be 1 equals 3 plus 2t. Okay, let's solve for t. Or t equals negative 1. So I can use either one of these parameters, s equals 3 in my first line, okay, or t equals negative 1 in my second line, and find this point of intersection. Okay, well, let's find it. Okay, when s equals 3. Okay, so that'll be the point. And I'm going to use my line, 0, 0, 0, 1, and I'm going to let my s equals 3, and I'm going to write the rest of my direction vector here, right here. That's negative 1, 0, and 0. Okay, so let's develop this. 0, 0, 1 plus negative 3, 0, 0. And let's get my point here, negative 3, 0, and 1. Okay, so is the point of intersection. Now I would have gotten the same point if I used the second line and the value for the parameter t equals negative 1. Okay, if I would have used the second line, t equals negative 1, I would have got, okay, negative 3, right? 0 and 1 as well here. So I would have gotten that same point of intersection here. Okay, I think that's it for the homework questions. Okay, make sure you follow the little mess up I did with the last example, this huge one. Okay, this huge one here. Make sure you don't write the equations down incorrectly here. The system is done and solved the same way. That's fine. Okay, but okay, please make sure that you're careful with these. Homework questions will follow. Okay, and if you need some extra practice, there's a mid-chapter review. Lots of questions in all these mid-chapter reviews, but we'll do these homework questions here, okay, on the homework page. Thanks and good luck.